Hello there. Welcome to this lecture about multispectral signatures, or colors as we may see them if the reflectance is within the visible part of the spectrum that our eyes can register. My name is Michael Runstrom. I work at Lund University as a teacher in geoinformatics and remote sensing techniques. We know now that electromagnetic radiation is emitted by all objects with a temperature above the absolute zero, which is 0 degrees Kelvin or minus 273 degrees Celsius. So all objects, the sun is 6,000 degrees and it emits a lot of energy or electromagnetic radiation, but also other objects, a house that is maybe 20 degrees is also emitting radiation in different wavelengths. And when that electromagnetic radiation meets with an object, it will either reflect or be absorbed, or parts of it will be absorbed and some of it will be reflected. And that is something we call the spectral reflectance. And we can see that as a percent unit of how much that is reflected based on the incident energy. We call it albedo also. And even if you haven't seen snow, maybe that snow looks very, very bright. So we have a very high albedo for snow. It reflects about 80–85% of the incoming radiation. Asphalt, on the other hand, which is our roads, will only reflect about 5–10% of the incoming radiation. Light soil will, depending on how much water it contains, reflect about 25–45%. Deciduous forests will reflect about 15–20%, coniferous forests about 10–15%. So when we look at these two types of forests, the coniferous forest will look slightly darker compared to the deciduous forest, that is then the leaf type trees. And that helps us to interpret if it's a coniferous forest and deciduous forest, maybe. We see also the electromagnetic spectrum here. We have the short wavelength here, the gamma rays and X-rays. And here we have the visible part of the spectrum, where we have the blue wavelength, the green wavelengths, and the red parts of the spectrum. And then we have longer wavelengths on this axis towards near infrared, thermal infrared, and radar, television, radio. So the absorption contra the reflectance properties of an object helps us to determine what kind of object we are looking at, and that is called the spectral signature. We can see the light coming into a prisma that is then divided up into different colors, the different wavelengths that we have. We see the rainbow pattern here. We have the blue parts of the spectrum, the green, the yellow, and the red parts of the spectrum. We see on the image a man walking with red trousers. And the incoming light on these trousers means that the blue wavelengths are actually absorbed by the material of the trousers and the texture, and the green parts is also absorbed by the material, the yellow ones as well, but the red parts of the incoming light is actually reflected by the material, and that is why we see the trousers as being red. We can also understand that if the trousers were wet, they would look differently. They would look darker because water absorbs the radiation. So if they were wet, they would have a darker appearance, but if they are dry, they will look red. So we use multispectral signatures over the whole space of the spectrum. We have here the visible part of the spectrum, which are then about between 0.4 to 0.7 micrometers. And we have the near infrared part of the spectrum here and the shortwave infrared here. So different objects have different multispectral signatures. We see water here reflects only about 5% here. This is reflectance here. Only 5% of the incoming radiation is reflected by water. The rest is being absorbed, and the energy is then transformed into warming up the water. Vegetation has a very special spectral signature. We see in the very short wavelength high absorption, low reflectance. We have a peak of reflectance at about 15 to 20%, and then we have an absorption of the red parts of the spectrum. And this is then why vegetation looks green to us, because more is reflected in the green part of the spectrum compared to the red and the blue parts. But if we look at the near infrared part, that our eyes cannot see that, but we can measure it using a sensor, we see a very high reflectance from vegetation. About 40–45%. And then we have a characteristics. These are water absorption minimas. So, but the spectral signature for vegetation has a very characteristic pattern. And that is how we use remote sensing techniques. We look for objects that look like a spectral signature. This is the soil spectral signature, but that of course depends on the content of minerals of the soil and also the moisture of the soil. We have a rock spectral signature here. So this is what we are using then when we try to determine what kind of object are we actually looking at from a distance, which is then remote sensing. And the spectral reflectance depends not only on the object, but also on the soil type and soil moisture. So if we look at different vegetation stands, the surrounding soil type and soil moisture will also affect their reflectance signal. The slope and the aspect will also affect it. The weather, atmospheric conditions will affect it. How much water vapor do we have in the atmosphere? That will maybe be different between two different times. Shadowing effects, if we study trees, for instance, trees will cast a shadow on the ground. That will also affect the signal that we are registering. The date and time of observation, the direction of observation relative to illumination. So, what can we conclude from this lecture? We now understand that difference in multispectral signatures provide possibilities to interpret what we are looking at. What kind of object are we looking at, for instance, on the Earth's surface? When we study it from a satellite sensor, for instance. So we try to understand and interpret the signal based on the multispectral signals. See if it looks a bit like the healthy vegetation signal, for instance. We have a possibility to classify objects at pixel level using automatic classification algorithms that will analyze if the multispectral signal for a pixel looks like a, a spectral signature that we have fed into the algorithms. Is it a vegetation type signature or is it a water type signature? So the software can then help us to classify a pixel, if it's water or if it's a deciduous forest stand or if it's an urban area, for instance. And we see the multispectral images here. There are 4 images here. That's one it's one image, but it's split up into different wavelength bands. So we would have then typically the blue wavelength band here, the green wavelength band here, the red one, and the near infrared one. And together, by looking at a pixel through these different wavelength bands, the computer can analyze to see if it looks like a healthy vegetation pixel or if it's more like a water pixel or something like that. If we have time series of satellite images, that provides a mean to study changes. What has occurred between these 2 years? Maybe in a pixel it was classified as vegetation. The multispectral signature looked like vegetation pixel, but then after 10 years the same pixel looks like just bare soil, and that would mean that the vegetation has died or been removed, and now instead 10 years later it's just soil there, and that would be then a degradation maybe, or a land use change or something. Okay, I hope you have enjoyed this lecture and good luck with your studies. Bye.